Well, to move on to the experiments, I'll take Abbe out of the back focal plane, turn the light down a little bit for the moment. I'll leave his name just for the moment. Take Jena away, take Carl Zeiss off the stage, and replace Carl Zeiss as the object with a series of lines, a diffraction grating in fact, which we're going to use as the object, the specimen, for these experiments. Up at the top we have a fine grating. The lines are on the slide about 8 micrometers apart, and at the bottom what I'm going to call the coarse grating with lines about 16 micrometers apart. Before we carry on, I need to focus my condenser on the illuminated field diaphragm like that, and since we'll be using it in the lower half of the lower part of the screen, I'll lower it down a little like that. So there we have that ready to go. And strictly speaking, up at the top of the screen you should be seeing a diffraction pattern of the grating that lies at the bottom. Now it doesn't look very much like a diffraction pattern because what it is multiple images of whatever is in the first focal plane of the condenser, which is, as you see, just an image of the filament. If, on the other hand, we put in a pinhole into the first focal plane of the condenser, and then, because much less light comes through, turn the lamp up, you now begin to see the familiar diffraction pattern. There on the screen you can see the 0 order in the centre and the first and the second and the third order beams to the left and to the right. We can have a look at the difference between the diffraction patterns from the coarse and the fine grating. If we look at the coarse grating there, you see that the widely spaced lines in the object and the final image at the bottom of the screen are associated with closely spaced spots in the diffraction pattern. And moving now to the fine grating, you'll see that the finer lines give you wider spaced spots in the diffraction pattern. Notice also that the first order of the fine grating, as you see there, falls on top of the second order of the coarse grating. There's a 2-to-1 relationship in the spacings in the object. There's a 2-to-1, an inverse 2-to-1 relationship in the spacings in the diffraction pattern. So there we see the diffraction patterns of the coarse and the fine grating. I'm now going to show you the effect of altering the effective aperture of the objective lens on the image quality. I need just to make a few little adjustments here. I'll put into the back focal plane of the objective, and in order for you to see it I'll take the pinhole away. In the back focal plane of the objective I've put in an iris diaphragm. If we go back to the pinhole, I'll check that they're concentric, and they are, and you'll see that as I close down the iris diaphragm in the back focal plane of the objective, I can take away parts of the diffraction pattern so that we're left simply with the 0 order as we see there. Or we can allow the first order of the coarse grating to come through, the second order of the coarse and the first order of the fine, and so on. So what this will enable us to do is to explore the contributions of these various diffracted beams to the final image. There we have both coarse and fine gratings visible in the image, and I'm going to close down the diaphragm. Watch what happens. At around this position we've lost resolution in the fine grating. I'll then move on, and you'll see that we then lose resolution in the coarse grating. Here now we have only the 0 order from which the image is being built, with no fine detail in the lines of the grating being resolved. Open it up, the coarse comes first, and then comes the fine, and you notice that the return of the resolution coincides with allowing the diffracted beams to pass through the diaphragm in the objective. It's more clearly seen if we simply look at the fine grating and close down the diaphragm. You'll see the resolution disappears as we remove the contribution of the diffracted beams to the image. Remember, Abbe's theory tells us that it's the diffracted beams that carry the information about the fine detail in the specimen up to the image, and of course if you don't allow these diffracted beams to pass up the microscope to reach the image plane, then the information about the fine detail doesn't get there either. There then you see the influence of aperture, objective aperture, on resolving power.